All right, so I'll do this one. Now, I chose this one on purpose because this is about ice hockey, and I'm assuming that almost no one here at BYUH knows anything about ice hockey. So it's great. Okay, so let's read it. So ice hockey star Bruce Blades is 5 meters from some blue line, and he's gliding toward the blue line at 4 meters per second. By the way, ice, in Physics 105 and 106, what is ice? No friction. Okay, it's an idealization. Okay, so Bruce is 5 meters from some blue line, gliding at 4 meters per second. Now you are 20 meters from the blue line, way back over there. And you're behind Bruce, and you want to pass the puck to him. So what speed should you shoot the puck down the ice so it reaches Bruce exactly as he crosses the blue line? Okay? Wow. All right, now, let's do it. Okay, so you kind of think about it, right? I'm visualizing a blue line over here, and Bruce is, close, and he's going that way, and we are way back here. We're behind, and, we want to smack that puck so it, goes that direction, all that. All right, so let's draw the motion diagram. Okay, so motion diagram. Let's just do Bruce first. Now notice, Bruce is skating on ice. There's no friction, so there's no acceleration, right? He's going to go at constant speed. So here's Bruce's motion diagram. He's moving to the right. Okay, I'm saying this is the blue line, huh? Blue line, get it? Okay, that's the blue line. He's moving to the right towards the blue line. Okay, now obviously, and he's going at 4 meters per second. Now we know that the puck is going to have to go a whole lot faster than 4 meters per second, right? Okay. So anyway, so there's Bruce going towards the blue line, acceleration 0, nice motion diagram. So again, this is just all this does is just help you start to visualize things, You draw the motion diagram, a equals 0 to the right, so velocity is positive, just stuff like that. Okay, okay, so that's one object, right? Bruce. Now, what's the other object? Is it you or is it the puck? What's the important thing, you or the puck? The puck. You're irrelevant, sorry, but it's true, all right? The puck is the object, right? That's what's moving, Okay, so now we want to draw the motion diagram for the puck. Well, if Bruce is here, and this is 5 meters, and the puck is 20 meters, so it's over here somewhere, right? Okay, so there's the puck over here. And again, the puck has to be traveling much faster than Bruce. But it's on ice, so uniform motion, right? Uniform motion. So again, acceleration is 0. All right, so that's the first thing you want to do. Draw the motion diagram. Okay, now we want to draw what's called a pictorial representation. And so we want to ask ourselves, how many points do we need to describe the object's motion? I mean, typically, you just need a beginning and an end if nothing changes. If something changes, you might need a point in the middle, where something changes. But here, nothing is changing. Here, nothing is changing. So all we need for Bruce is a beginning point and an end point. For the puck, we need a beginning point and an end point. Okay? All right, so there it is, right? So for Bruce, we have a beginning point and an end point. For the puck, we have a beginning point and an end point. Now remember, we want to know we want the puck and Bruce to cross the blue line at the same time, right? So that's why the puck and Bruce are right there. Okay, now, you have to choose an origin. We're going to make measurements, right? So you need an origin. So where you put the origin is completely arbitrary. You put it wherever you feel like it. And I'm going to put it here. Why? Why not? I mean, who cares, This is positive, that's negative. If I were to put the origin here, this would be a negative position. I don't like negative positions, So I'm going to put the origin here. All right, Bruce. Okay? Now, how do you describe motion? Position, velocity, acceleration, and time. Yeah? Okay. So that means, sorry to tell you this, for every single one of these locations, the beginning and the end, you want to put a variable for position, velocity, acceleration, time. Ugh. Now, what's nice about it, we drew this motion diagram. Acceleration is 0. Don't have to worry about that. All right, so here you go. Ready? So here's the origin. This is the puck. So x, now, come on. There's x puck, there's x Bruce. You got to differentiate them, you know? So we're going to say x sub p. That's a p there. Probably can't see it, right? xp, x puck, xb, x Bruce. Now this is the initial point for the puck, so we're going to say xp0. This is the initial point for Bruce, x Bruce 0. Right? Then you just do it. You know, position, velocity, time, because we don't have to worry about acceleration. So x puck 0, velocity puck 0, time 0. That's a t, believe it or not. Okay, x Bruce 0, velocity Bruce 0, time 0. Okay, now over here, so we're going to call the initial point 0. Might as well. I mean, you know. So we're going to call the initial point 0, and we're going to call the initial point 1. Do you have to do that? No, but why not? Okay, so x Bruce 1, velocity Bruce 1, time 1. X puck 1, velocity puck 1, time 1. That's it. Okay, now, okay, so this is fine, but now what you're going to do, for every single one of these variables, you have to figure out what they are. And if you don't know what they are, I mean, you're not going to know what they are. You're not going to know all of them. I mean, that's the whole point of the problem, right? We're supposed to find the initial speed of the puck, right? We're supposed to find that. Okay, so what we got to do is we're going to figure out everything. So every single thing here, you should have listed over here. Let's do it. So x puck 0, I said that was the origin. That's my decision. So there, x puck 0 is 0. All right. Okay. I do it differently than Randy Knight, right? I just get all of these 3, all of these 3, all of these 6, but he doesn't. So I'll just follow him, whatever. Okay. No, I'm going to follow me. Forget it. X puck 0 is 0. Velocity puck 0. So what's the speed of the puck? That's what we want to know, right? That's what we want to know. So velocity puck 0. Now, I don't write find. I usually just circle it or something like that or put a question mark. I always circle it because I want to, when I'm working the problem, I want to remember what am I trying to find. So I always circle this thing so I know what I'm trying to find. Okay, what's time 0? Well, what do you want time 0 to be? 0. I mean, you don't have to, but it seems to be the logical, easy thing to do, right? So we'll just say time 0 is 0, huh? So time 0 is 0. Okay, we got that done. Done. Now we go over here. X Bruce. Okay, now you got to think. This is 0 meters. This is 20 meters, right? This is 5 meters. So what is x Bruce relative to the origin? 15, right? Okay, so x Bruce 0 is 15 meters. What's velocity Bruce? Says right there, right? 4 meters per second. Right? Velocity of Bruce doesn't change, 4 meters per second. I already said time 0 is 0. I don't have to worry about that. Right? So I got these 3, got these 3. Okay, what's x Bruce 1? 20, right? So that's what we, right? X Bruce 1 is 20. What's velocity Bruce 1? Remember, Bruce doesn't change. Bruce is always going at 4 meters per second. So velocity Bruce 1 is 4 meters per second. What's the time? What's time 1? Do we know time 1? No, we don't. So if this were me, I would write here time 1 equals question mark, because I don't know it. Okay, we're done these 3. Let's go here. What's x puck 1? 20 meters. So x puck 1, 20 meters. What's velocity puck 1? That's what we're trying to find out, right? Because the velocity of the puck doesn't change. So velocity puck 0 is the same thing as velocity puck anytime, right? So, all right, so I don't know that. What's T1? I don't know T1. Okay, so what I'm saying is everything here should be defined here, either with a value or a question mark, all right? And again, you want to somehow emphasize that this is what you want, okay? All right. Okay, so we're not going to solve it for this one. We just want to set it up. I guarantee you, I know I've said this at least twice before, if you do this right and you don't make a silly algebra mistake, you'll solve the problem correctly. So make sure you understand this, okay? Spend some time on this. Make sure you understand it. Oh yeah, okay, so you read it twice, you think about it, you visualize it, you draw the motion diagram, you draw the pictorial representation, you define everything, you know, after, right? This takes time, all right? Then you're going to, I'll show you later, but you're going to figure out which equation to use, one of the kinematic equations. You're going to solve it, total piece of cake, you know, easy algebra equation. And then you're going to assess. Now, you got to do this. You always ask yourself, is my answer reasonable? So I had a student years ago. They were supposed to find the height of a tree. Now the student came up with a negative answer. All right. So the student said something like, I mean, you know, I saw the work, right? So I'll just make this up. So the height was minus 10 meters, right? Now, come on. If you were supposed to find the height of a tree and you get minus 10 meters, what would that signify? You did something wrong. Well, what did the student do? Just erase the minus sign. Not a good thing, right? All right, so you always want to ask yourself, does the answer make sense? Let's say, listen, right? You're supposed to find the speed. So let's say you did all your work, and you were a good student, you kept your units and everything like that, and you came up with something like this. Velocity is 2 meters per second squared. What does that tell you? You did something wrong, because its speed should be in meters per second, right? So you always want to ask yourself, is it reasonable? What if you came up with something like a million meters per second? Well, that's crazy. Or like 0.00001 meters per second. It's crazy, you know? So you always want to assess, okay? If you're a pre-med student, you better assess. We talked about that the other day, right? Because if you make a mistake, you could kill somebody. All right. Now, something else which is important. So you're going to have an algebra, you're going to have an equation here, right? One of those kinematic equations. The best problem solvers always wait until the very, very end before they plug in their numbers. So you always want to work with the variables here, okay? And then you plug in your numbers last. Why? Well, number one, if you just do the algebra first, sometimes things cancel. So you're actually saving time, you know? Number two, for most people, it's much easier to check an algebraic equation than it is to check things with numbers in it. So try to, if you're not used to that, just try it. Do the algebra first, then at the very end, plug in your numbers. All right, let's do some more examples. Okay, so read it twice. All right, so Billy drops a watermelon from the top of a 3-story building. I'm picturing in my head, you know, 10 meters above the sidewalk. How fast is the watermelon going when it hits the ground? So I'm picturing it, right, this kid dropping a watermelon. Hope nobody's around, right? Okay, now, 10 meters above the sidewalk. Okay, do they tell us anything about air resistance? No, so what do we have to assume? I mean, we haven't even talked about it. We haven't even studied air resistance. So we're going to assume this is free fall. You have to, okay? Now, what I want you to do is pause and draw the motion diagram, draw the complete pictorial representation, which includes, you know, all your variables and then define all your variables. So all that work. Okay, we're back. All right, so here is the motion diagram. So it's free fall. So, you know, starts out at rest, gets faster, 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 faster. Okay? And so the acceleration points down, right? Acceleration points down, like we talked about earlier. Okay? Now, how many points do we need for our pictorial representation? Well, you know, I mean, all we need is a beginning and an end, right? We have constant acceleration. So we just have a beginning point, which we'll call 0. We have an ending point, which we'll call 1. If you don't like that, you don't have to. You could have called this point A, point B. It doesn't matter. Okay, it just doesn't matter. I didn't say this last time, but I should have. You always want to do this. This just reminds you of the positions and the signs. Okay, so all we care about is vertical motion, so I'm going to say down is negative, up is positive. We'll do that for a while, but we're going to get to a point where we change our mind. So we're going to have positive, negative later on. So this is just a good reminder, all right? It's a good thing to do, so I recommend you do it. All right, so here we go. Now we know that the acceleration is constant, so that's fine. Just label it. Just tell your brain acceleration is constant. Okay, so we have position, velocity, acceleration, time. We have acceleration here, so we just want position, velocity, time. Position, velocity, time. There's only one object. We don't have to get all picky with subscripts like we did in the previous one. So what do you want to call the origin? Well, whatever you want. I don't care. What do you want to call it? Where did I call it? I don't know. Let's see. What did I call it? I call the origin here. Why? I don't know. Who cares? It doesn't matter. Honestly, it doesn't matter. If this is going to be the origin, though, and you're using this coordinate system, this would be a negative, right? Negative position. I just don't like negatives, right? It's just me. So I'm going to call this the origin. Why not? Okay. So if I call this the origin, then this is at 10 meters, right? So y0 is 10 meters. Okay, velocity, initial velocity is 0, right? We're dropping from at rest. And time 0 is 0. Why not? You know, time 0 is 0. Okay, this is acceleration due to gravity, minus 9.8 meters per second squared. Got it. Now we go down here. What's y1? It's the origin, so it's 0. v1, that's what we want to find. So if it were me, I would circle this, you know, make a big circle around it. And what's t1? Well, I don't know. So if it were me, I would put t1 equals question mark. I might need to find it. I might not need to find it. I don't know. But everything here, I'm going to write down here. Okay? All right. Now, let's see. Okay, so now, yeah, I sent everybody an email, and I sent them this handout, and I said, you want to print this or somehow have it available, because you're going to refer to it all the time. Okay, so here are your kinematic equations, right? And we're doing free fall, so we want to look at this. Okay, we want to look at this. Now, let's go back. What do we know? We know the distance, right? 10 meters. We know the acceleration. We want to find the velocity. We don't know anything about time, right? We don't know t1. So we don't know time. So we want to find velocity. So you got to kind of keep this in your head. You want to find velocity. Okay, so what's the velocity? Okay, now you know the distances, right? You know the distances, right? You know y0 and y1. You also know a. You don't know time. Don't know time. Okay, so then you look at these equations and you ask yourself, wow, which equation would be the appropriate one to choose? This is not going to help me because this requires time. So I don't know time. I can't use this one. This is not going to help me either because you have to use time for this one. This is the one that's going to work, right? Because look, I know delta y. I know the initial speed. I know g, right? It's g, you know. This is the final speed. So this is the equation I'm going to use. So this is kind of the key, you know. That's what's so great about drawing your pictorial representation, because then you realize right away what you know and what you don't know. And then knowing what you know and what you don't know leads you to choose the correct equation. Okay, so the correct equation is that last one. So v final squared equals v initial squared minus 2g delta y. I didn't bother writing the y and the y because I know it's a y, so why bother, you know? Okay, now go back to this. By the way, I'm going to do these things the long way. After a while, you'll start taking shortcuts. So it's okay. So this is my initial point, y0. This is my final point, y1. So I have v1 squared equals v0 squared minus 2g. Now, what's delta y? Remember, what's delta anything? Final minus initial. So it's y1 minus y0, okay? Delta y, y final minus y initial. All right. Now, what I usually do at this point, anything that's 0, I throw away. Okay, so anything that's 0, I throw away. So what's 0? Well, this is 0, right? Okay, y1 is 0. Throw that away. Okay? So now I have v1 squared equals minus times a minus is a plus. So I have 2gy0. So therefore, v1 equals plus or minus square root of 2gy0. Okay? And, all right, so v1 equals plus or minus square root 2gy0. Okay, and first of all, things going this way. So you have to make the choice. Is it going to be a positive velocity or negative velocity? Negative, right? That's what's nice about this. It reminds your brain, hey, negative, not positive. So negative square root 9.8 meters per second squared. Okay, what's y0? See, this was great. Once you get your equation, everything you need is right there. You don't have to read the problem anymore. Just look at what you wrote here. So then it's 10 meters. Okay, notice, what's the units? We have a meter times a meter. So we have a meter squared. We have a second squared on the bottom. We have a square root of that. So it's a meter per second. Isn't that what we want? Yeah, it's a velocity, right? I promise you, if you do this, you get minus 14 meters per second. Okay? All right, now, okay, any questions? Now, I got to point out one little thing. So I solved for the velocity, right? Because I have the negative sign, shows the direction, and I have the speed. The question actually asked for how fast is the watermelon going? Now that's a speed question, right? So the correct answer is actually just 14 meters per second. Okay? Be careful. You know, that's what I mean. If it were me, I'd underline or I'd circle that word fast. How fast is it going? Because it's speed. All right? Okay. Now we want to assess. Well, do we have the right units? Yeah. Does this number seem reasonable? Yeah. It's not like 1,000. It's not like 0.001. I mean, it seems reasonable, right? So we're good with it. Okay. Now, there's something that's important here. And this is not physics, it's English. The question says, how fast is the watermelon going when it hits the ground? It's not moving at all when it hits the ground, right? Well, that's not what they mean. What they really mean when they ask a question like that is, how fast is the watermelon going when it's like a billionth of a centimeter above the ground, okay? So they want to know how fast it's going is right before it hits the ground. So you have to understand that. All right, so this was considered an easy question, an easy problem. Please work on it by yourself. Make sure you understand it. Okay, let's do another one. Let's do another one. Oops. Oh, yeah. Okay, read that twice and think about it while I'm erasing. Okay, what's the answer? You should know the answer already. You don't have to do anything. Sally is 1,500 meters above the ground. She descends at a steady speed of 5 meters per second. How long does it take her to reach it? Well, distance equals rate times time, right? Distance equals speed times time. So 300 seconds times 5 meters per second is 1,500 meters. So all I'm saying is, come on, we know the answer, right? The answer is 300 seconds, okay? But we are trying to get practice doing this Randy Knight problem-solving strategy, okay? So we got to draw the motion diagram and the pictorial representation, the whole bit, just to get practice. So everybody pause your video in a minute and draw the motion diagram and draw the complete pictorial representation. Okay, so we're back. So it says steady speed, right? So again, if it were me, I would underline or I would circle the two words steady speed. Because, if you miss that, you miss the whole problem, So you want to look for those adjectives, steady, all right? Okay, so steady speed, here's your motion diagram, right? Steady speed, so the acceleration is 0. Okay, how many points do you need? The beginning point and the end point. So there's your beginning point, y0, v0, t0, your end point, y1, v1, t1. We're going to use this coordinate system for quite a while, so just write it down. We'll choose this for the origin for no good reason. Okay, so here we go. So y0, 1,500 meters. Now here's something you've got to be careful of. The initial velocity. It's 5 meters per second, but it's going down. We're using this coordinate system. So velocity initial is minus 5 meters per second. That's one thing that's nice about always drawing this, because it just reminds your brain, So many people, especially students learning this from new, they forget the minus sign. So this just kind of helps you remember to put the minus sign. Okay, t0 is 0, no kidding. Okay, y1 is 0 because we chose it to be the origin. Okay, how long does it take her to reach the ground? Again, what we're saying is like a millionth of a centimeter before it hits the ground, right? And so she's still moving at that minus 5 meters per second. Okay, it's not 0. And what we want to know is the time. So I circle that. So I'm telling my brain, that's what you want. Okay? So look, what do we know? We know the distances. We know the velocities. And we want to find the time this time, right? We want to find the time. So here's your equations. So which equation are you going to use? What do you think? Well, oh, sorry. Okay, which equation are you going to use? So the acceleration is 0. Okay, so let's just go through it. All right, the acceleration is 0. So is this going to help us? Not at all, because this will go to 0. We want to find the time. Is this going to help us? Not at all. So we have to use this long one. Ugh! Right? Got to use the long one. Oh my gosh. Sorry, it's what you got to do. Sometimes life is tough, right? So you got to use the long one. Okay, so here we go. So let's see. Write it down. So y. Okay, now let's be a little lazy. What do you say? Save a little time. So the final one is going to be the 1, and the initial one is going to be the 0. Okay? So we're going to have y. So again, we're using this long one. Or this one, doesn't really matter. So y1 equals y0 plus v0 y delta t. And here, this is 0, right? Because it's not free fall, right? This acceleration is 0. So that's all we have. Awesome. Okay, now let's put in our zeros. Okay, what's y1? y1 is 0. Okay, so we have 0 equals y0. And what's delta t, by the way? Delta t is final minus initial, so it's that. Agree? And what's t0? 0. All right, so we just have 0 equals y0 plus plus v0, and then t1. Okay? Any questions? So we do the algebra first, all right? Get that in your head. Do the algebra first. So I'm trying to solve for t1. So I have minus y0 equals v0 t1. So I have t1 equals minus y0 over v0. Nothing canceled, but it didn't hurt. Well, sometimes it's going to cancel. So do the algebra first. So now, again, everything you need is on your picture. So what's y0? Look at 1,500. So we have minus 1,500 meters. V0 is minus 5 meters per second. and you have a minus over minus, which is a plus, and you have a meter divided by a meter per second, so you're going to have a second, so it's 300 seconds. Okay? Is it reasonable? Yeah, we know it's the right answer. Okay, so make sure you know that. Make sure you understand it. Has that been a half hour? Let's quit. We have a couple more problems to do, but let's quit now.